Okay, everyone. Topic 3.1 is intermolecular forces, and how you're going to see this written is IMF. Okay, so when we're talking about IMFs, we're talking about intermolecular forces. Now, before I dive into these different types of IMFs, we just need a reminder about the difference between intermolecular and intramolecular. Inter means between molecules, where intra means within molecules. So an intramolecular force is a polar covalent bond or a nonpolar covalent bond. Okay. So you can have polar covalent bonds or you can have non-polar covalent bonds. That's what's holding the atoms together inside of a molecule. Molecules are covalently bonded. We could also have interactions between ionic things. And so if we have a metal and a non-metal, that would be an ionic bond. But if it's a non-metal atom and a non-metal atom, then that's either polar covalent or non-polar covalent, and those are our molecules that are covalently bonded. What about some attractions between molecules? So here's a water molecule. We can add our lone pairs on there. Here's another water molecule. And the bonds inside of the molecules, the intramolecular forces, covalent and non-polar covalent and polar covalent bonds, those are much stronger than the intermolecular forces, the IMFs. But there is still attractions between molecules. Okay, so a good chunk of the AP Chem test is these IMFs and being really familiar with them. And it's going to be based on identifying if something's an ion, if something is a polar molecule, or if something's a non-polar molecule. Because here's the different types that you need to be able to distinguish between. So if you have an ion and a polar molecule, oh, I said compound, this should be molecule. Okay, there as well, molecule. So if we have an ion and a polar molecule, then the force of attraction between those things is going to be what we call an ion dipole force. If we have an ion and a nonpolar molecule, then what's happening in between is called an ion-induced dipole. If we have two polar molecules, then the force of attraction between those polar molecules, just like the water molecules, these are both polar, and so this IMF that's between them is a dipole force. And hydrogen bonding is a special kind of IMF that I'll go into more detail in a little bit. And then we have London dispersion forces. Okay, this occurs between two non-polar molecules. So let's look at each of these scenarios and talk through this really quick. Ion dipole. Okay, so we need to be able to identify the dipole. All right. We need to identify the ion. So one of two things. Either it will completely show you that it's an ion, like magnesium, and it'll be like 2+. So it'll be like really clear. It's got a positive or it's got a negative with it. Okay? The vast majority of the time, that's what we see. It'll put the plus or the minus with it. Occasionally, it might say magnesium chloride, MgCl, and you need to recognize, oh, this is a metal and a non-metal, and so that would be ionic. So when we have an ion, the magnesium or the chlorine, and in this same space there is a polar molecule. Okay? polar molecules, all of the domains are, something's off. They're not the same. Like, one thing is different there. So an example of this is pH3. Okay, this has 4 domains. 1, 2, 3, 4. But one of them is not the same as the other one. That's asymmetry. So that means that this is a polar molecule. And it turns out that if you have an ion and a polar molecule, there will be an attraction between them. Okay, there will be an attraction between them. And this attraction between them, this IMF, we call an ion dipole force. Okay, an ion dipole force. Now, how would these polar molecules arrange around these ions, though? And this is an important part. The lone pairs are a large negative region. And then also, if you look at phosphorus location on the periodic table versus hydrogen, these are polar covalent bonds. Like, the phosphorus has a higher electronegativity than the hydrogen. So the electrons are headed that direction. So this is the negative region of the molecule, and these hydrogens are more positive. So the positive sides are going to have an attraction to a negative ion. But if I'm drawing another one of these molecules around a magnesium, this is positive, and so it's going to be that more negative phosphorus and the lone pair. That's where we're going to see the attraction is there. Okay. The most common one that I see is a water molecule, though. So everyone, let's be really, really clear on this one. What if I have a water molecule? This is polar, okay? Polar molecule. There are 4 domains, 1, 2, 3, 4. 2 of them are different than the other 2. They're not all the same. So we get this asymmetry. So this is a polar molecule. This is the negative, partially negative region, and the hydrogens are the partially positive regions. So I saw a question where they showed, probably like, we'll do magnesium again. They showed a magnesium ion, and then they asked the students to draw the water molecules around it. And remember, positives attract negatives. So what we would want to see is that the oxygens are kind of surrounding that magnesium, not the hydrogens. Okay? And that attraction between the ion and the polar molecule is an ion dipole force. Okay. And during class, we're going to talk about when these ion dipole forces are stronger and when they are weaker. So instead, I'm going to have us now move on to an ion-induced dipole. So we know that if we have an ion, let's pick a new one, potassium. Okay, great. I have an ion, and induced dipole means that the other thing was a non-polar molecule. So an example of a non-polar molecule would be CH4. This is also 4 domains, and they're all the same, so we get symmetry. So there is an attraction between this molecule, really anywhere on this molecule, and the potassium. There is an attraction. It's not as strong as the ion dipole interaction, but that would be an ion induced dipole, IMF, intermolecular force. Okay, there's so much identifying of this. So if we have an ion and a nonpolar molecule, we get an ion-induced dipole. Something I noticed on your last test, please, if you have hydrocarbons, these are molecules that contain only hydrogen and carbon. Doesn't matter how much, but they're only hydrogen and carbon. Those molecules are always nonpolar. So I'm not really worried about what the shape is. As soon as I see that I have an ion and then some molecule that, let's just say C3H, 1, 2, 3, 4, 5, 6, 7, 9, is that right? 6 and 8, okay. C3H8, however that structure looks, doesn't really matter because it's a hydrocarbon. So any attraction between those two is an ion and then an induced dipole. Okay, so ion dipole, that means an ion and a polar molecule. That is a stronger attraction than an ion-induced dipole, or an ion that's attracted to a nonpolar molecule, right? Our next is dipole, okay? Dipole is two polar molecules. Polar molecule. Okay. Now, water shows up so much. Please do not forget that water is a polar molecule. The reason why it's a polar molecule is because it has 4 domains and we get an asymmetry. Not all of the domains are the same. And so this is far easier to see when we draw it like this. It's not wrong to draw it like this, but it's hard to tell that it's asymmetrical in 3D space. It looks symmetrical here, 2D, but 3D it's actually supposed to be. It's actually asymmetrical, so it's a polar molecule. Okay? So if I have this water molecule, and remember, this is my positive region and that's my negative region, it will have an attraction to another water molecule, another polar molecule, and the positive end will attract to the negative end. Okay? This is a dipole IMF, right? Now, anytime you are recognizing that it's a dipole, there's another IMF that's also happening that I'll describe in more detail in just a moment. So there's dipole, and there's London dispersion. Okay, dipole, and London dispersion. Again, dipole means that it's an attraction between two polar molecules, right? Not as strong as our ion attractions, but one of the stronger IMFs. Alrighty, nice. So we have a question here. Can a dipole IMF intermolecular force form between BF3 and HBr? Let's see. Boron, 3 fluorines. Now, fluorines have 7 valence electrons. So right now it's only being assigned 1. So we have 1, 2, 3, 4, 5, 6, 7. That's what we'll have around the rest of them. Boron, based on its location, it's only got 3 valence electrons. 1, 2, 3. But remember, boron, beryllium, and aluminum are the suboctet atoms. It's okay for this one to have less than 8. All of these have a formal charge of 0. So there are 3 domains, and each domain is the same. So this is a non-polar molecule. HBr is a polar molecule. Because notice, if bromine's in our middle, like we count that as the center, there are 4 domains. 1, 2, 3, 4. 3 of the domains are the same, but 1 is different. So we get that asymmetry. So this would be a polar molecule. So can a dipole-dipole IMF happen between these? Nope. A dipole-dipole IMF cannot form between those. What we would actually see is an induced dipole with a dipole. Induced dipole is reserved for nonpolar molecules, and polar molecules have dipoles. So the attraction that would happen between these two would not be dipole-dipole, it'd be induced dipole-dipole. Okay. Last item in this video, and then we'll have more that we'll definitely be talking about in class. So, hydrogen bonding, okay? First things that we need to know. So, if a molecule has a fluorine, an oxygen, or a nitrogen bonded to hydrogen, okay? So, like fluorine, oxygen, nitrogen. If one of those atoms is bonded to a hydrogen, okay, so here's an example, NH3. Okay, so first thing for hydrogen bonding is that one of the 2 atoms has a hydrogen bonded to either fluorine, oxygen, or nitrogen. Okay, the second thing that has to happen is the other atom needs to have a lone pair. It's less that it's on, and so let me cross these out. A lone pair on fluorine, oxygen, or nitrogen, it's less that it's on fluorine, oxygen, or nitrogen. It's more that the other one just needs a lone pair, honestly. So this is interesting. If I have NH3, and then we have another NH3. This meets the criteria for a hydrogen bond. So between them, we can have a hydrogen bond. And the reason why this works is one of the molecules has a hydrogen bonded to a fluorine, oxygen, or nitrogen, and the other one has a lone pair. That's why the hydrogen bonding works. What if, over here, what if I have another molecule, and let me pick one where it doesn't quite, okay. PH3. Okay, so not nitrogen in the middle, phosphorus in the middle. Phosphorus is not fluorine, oxygen, or nitrogen, but it does have this lone pair. So this could also be a hydrogen bond. Okay? One of the atoms has to have a hydrogen that is bonded to either fluorine, oxygen, or nitrogen. The other atom needs a lone pair. This one has the lone pair, so that could also be hydrogen bonding. Okay, We will talk more about hydrogen bonding during class, but just like dipole, whenever you have hydrogen bonding, we should probably also we'll also have dipole and London dispersion. Okay, so hydrogen bonding, dipole, and London dispersion. London dispersion can be all by itself. Dipole cannot. It will always be partnered with London dispersion. Hydrogen bonding cannot be by itself. As soon as you have hydrogen bonding, you also have dipole, and London dispersion. All right, guys, make sure that you also get the pictures from the lab put onto your digital lab notebooks. So make sure that's added as well. All right, thank you everyone for your hard work.